All right, guys. So today is going to be a pretty patient lab, if you know what I mean. I'm sure you guys all read the pre-lab material, or at least, grazed over it. It's very wordy and lengthy, and I'm going to do the best I can right now to make it not so much like that. So before we get into it, though, I wanted to go over one or two things from last week. Who had a quiz last week that asked about there being a final sample with 600 milligrams or grams of products? Anybody remember that? Well, some people here, and we noticed it, there was a certain question, I forget which form of the quiz it was, but it was about how there was, this much percentage of species X, this much of Y, they come together, and then they actually give the information that there's 600 grams of products. And what it was asking for was not the empirical formula, but the chemical formula, the molecular formula. And that, if you guys remember, is not the same as an empirical formula. Okay? So the big trip up that I saw in that question was that people would narrow it down to the amount of moles that there were of each one. And that was all well and good. But then some people went one step further and then divided by the lesser of the two number of moles, and that right there is where the error took place. Because that's for an empirical formula. A molecular formula, you can base it strictly off of how much of each thing that you have and how much product that you have. Okay? So I'm just saying this out loud so that if any of you go back and look at your quizzes or whatever, and you happen to see this and you wonder what went wrong, that's what might have gone wrong. The other thing, the post-lab from last week. The post-lab had some kind of tricky significant figures. So, with maybe the exception of like one or two people, and even that would be a lie, everybody lost like at least a half a point on the post-lab because there was somewhere along the line an error in the use of significant figures. So, we're going to try again this week to get it straight and to get it right, okay? I think it's going to be a little bit easier to do that this week because if you look at your cover pages, we're asking for two things after all the work is done, okay? So there's not as much, of this and much of that you're gonna have all summed up at the end. It's all gonna lead to the exact same answer. So what we're doing today is an acid-base titration, and this is a form of volumetric analysis, okay? So before getting into it, just a little bit of theory. We have been working with glassware in almost every lab so far, but we haven't really talked too much about how they're classified. So when it comes to glassware, there are things called TD glassware and TC glassware. TD glassware, expanded, means to dispense. And what that means is that independent of how much you bring into the instrument, so long as you have it to the fill line that's marked, even if there are a few drops left at the end after you finish draining it, it's calibrated to dispense, in our case, 25 milliliters of fluid, okay? On the other hand, we have TC glassware, which is to contain when it's expanded. And so that's more along the lines of maybe a beaker or maybe a graduated cylinder. There's a guarantee that there's accuracy to what you have your liquid filled to, but there's not necessarily a guarantee that that exact same amount is going to be dispensed. Okay? On the other hand, if you have a TD piece of glassware, like the pipette we're going to use today, which is really unusual looking, there may well be more liquid in there than you thought, but you can be guaranteed that so long as you filled it properly, whatever is left over is there on purpose, because what's been dispensed is the amount that it says it will do, okay? So, in terms of titrations, titration is a method of quantitative analysis, meaning that it's not qualitative. We can actually generate numerical data for it, which is powerful. So, it involves the use of a titrant and an analyte. They are mixed together. So the titrant is the substance of the two, one of the two, that we know everything about. And what I mean by that is the volume of it that we have, the volume that we involve, and its concentration. Okay? The other one, the analyte, is the one where there is a variable. So in our case here, we're going to know the volume of our analyte, but we're not going to know its concentration. And that's the entire point of the lab. So we're going to be doing two titrations today. First, to find a secondary standard from a primary standard, and then to find, I guess, what we consider a tertiary standard, but we're not calling it that. So a primary standard is a substance that you can look up in literature and get an exact spiel about what it is. You know, it comes right out of a box or a jar or a bottle that you know exactly what it's about, its concentration. It's up to you how much of it you want to use. So it's a stable substance as a reference point. From it, we can generate a secondary standard. In our case today, the secondary standard is going to be sodium hydroxide. We're going to know how much volume we have, but we're not going to know its concentration until we do our first titration. Our primary standard is the oxalic acid, the hydrate form compound, but as soon as it hits water, it's going to slough off, and it's going to just be the oxalic acid. Okay. After we have found the concentration of the sodium hydroxide, we're then going to find the concentration of the hydrochloric acid we're going to use today. Okay? So you can see, we're just going to work down one by one, revealing the next thing after having revealed the first thing. Okay? So a couple other definitions that are relevant to a titration. So in our case, our titrant, again, is going to be the sodium hydroxide, at least when it comes to our trying to solve the concentration of the hydrochloric acid, which means that the analyte is going to be the hydrochloric acid. So what this means is we are adding base to acid. Okay. So I'm sure you guys have seen in lectures or in the textbook a titration curve. So here it is, and a couple things I want to mention about it. As you can see here, this is pH on the Y, and the volume of the titrant that's added on the X. And this is an example of a titration curve for a strong base and a strong acid. Okay? So what you can see here is we're going from low pH to high pH in a sigmoidal fashion. Okay? So what can we deduce from this? It's that when we're doing our lab today, we're going to have a whole lot of, nothing, and then suddenly, all at once, the change we're looking for is going to occur. And then, afterward, it's only going to become more of the same thing, not much change, okay? So, to spell it out really clearly, we're starting with our acid. We are titrating in base until it reaches a neutral point. And then we're actually, to a certain degree, going to go into a basic state. So the point at which the reaction has been neutralized and the pH is neutral, which would be about 7, is called the equivalence point. It's difficult for us to observe that because we're using clear reagents. So the way that we rectify that is we use an indicator. And so when the indicator, to personify it, realizes that the pH has changed, it is going to change color as well. So the indicator we're using, I have trouble pronouncing it. It's phenolphthalein. Yeah, phenolphthalein from the cameraman. And so what's going to happen is in clear and neutral environments, it indicates it's clear. However, the moment you enter above 7 into basic territory, it turns a violety purple. Okay? So, just to spell it out a little bit better, the end point is the moment when we realize that the change at the equivalence point has actually been realized. And so, if you look back at this curve again, the equivalence point is here, and the end point is really not going to happen until a little bit later. So what we have here is a degree of error. Luckily, as long as we do it the right way, it'll be a negligible amount. Okay? So we have error going this way, and we could potentially, if we really screwed it up, have error going this way. Like an extreme amount of extra fluid, extra titrant added. Okay? So there's the error. The last thing I want to say, we don't really have to use it in the lab today, but it's another way of analyzing information, is normality. Just like molarity, this is normality. And instead of it being moles of whatever we have over the liters of the solution, this is the moles of proton equivalents per volume that we're dealing with. So in our case here, we just assume that we have 1 liter. Okay. So as an example, if we had 1 molar hydrochloric acid, and we know that that contributes just 1 proton per per species. If we put that in 1 liter, we would know that it's 1 N, 1 normal, 1 molar, 1 normal. On the other hand, if we had 1 molar concentration of sulfuric acid, that's a diprotic acid, it has 2 protons to give away, that would be 2 parts of protons per liter, and that would be 2 normal. Okay, so that's all I want to say about theory. Today's experiment, as we said a second ago, we're going to first use a primary standard to develop a secondary standard. Then we're going to use the secondary standard to find out about our final unknown. So first what's going to happen is this neutralization reaction. We have 1 part of the oxalic acid dihydrate with 2 parts of sodium hydroxide. They're going to react as they're mixed together. And what we're going to be left with is this disodium oxalate, I think it might be called, and 4 parts of liquid water. Okay? So, to spell it out nice and clear, and not like the book does, what we have to do before doing any experimentation today is clean all the glassware with distilled or deionized water. Okay? So when I say the glassware, I mean every piece of glassware you were given. Okay? So the burette, the pipette, any beakers you were given, any Erlenmeyer flask you were given, a volumetric flask you were given, and a graduated cylinder. Okay? The reason for this is because these are very, very, very fragile reactions. If there's a contamination, it usually reflects, and on top of being a fragile reaction, it requires some good accuracy, so we don't want any contaminants in there that could mess it up. So after you clean your glassware with DH2O, you're going to go to the normal hoods that have the reagents, either that one or this one over here, and you're going to take 200 milliliters of sodium hydroxide in a beaker, and you're just for a moment going to set it aside. After you do that, what would be best to do would be to condition the burette. Now what that means is, after having cleaned it with the distilled water, to condition it is basically to give it a taste of what it's going to be holding. Again, just to eliminate contaminants. So, if we have our burette here, our burette's only going to be holding sodium hydroxide today. So, imagining this is full of NaOH, all we need is a little bit. Make sure the stopcock is closed. Now, you guys remember how to pour strong, dangerous acids and bases, right? Away from you, at waist level, and not pointed at your shoes or your legs, just in case. So all you need for the conditioning is just a smidge. So just pour a little bit of NaOH in there. You know, maybe like up to 48. So what you want to do here is, over the sink, you can bleed out a little bit of it, but not all of it. And the rest, what you kind of want to do is, imagining it sitting right here, you want to kind of invert it a little bit and swirl it and twist it, okay? This is going to make sure that all sides of the walls of the barrel of the burette get a little bit of the sodium hydroxide. You know, just kind of ease it, and then right into the sink, okay? And it's ready. So, after you've done that, you can then take it back in your hand and fill it up. And what I think is easiest, especially when we measure our volumes, is just to fill it straight to the zero etching at the top, okay? You'll get a lot of longevity out of it, and also, as I said before, it's easier to work with, you know, regular, you know, numbers like that. So, after you've filled it, after you've conditioned and filled it, then what you want to do is go to the scales where there is oxalic acid dihydrate in a solid form, okay? You want to measure out between 0.8 grams to 1 gram. No more, no less. It doesn't matter how much in between. We read electric scales to 3 significant figures. So let's say on the nose, you get a perfect 0.9 grams. I better see 0.900. Or it's going to, again, be an error. It's going to be a mistake. All right? So after you have that on your little piece of weight paper, you want to pour it into the Erlenmeyer flask. This is going to be our reaction vessel for the course of today. Okay? So pour the solid in, then add 40 milliliters of distilled water, and then go back over to the reagent hoods and take 2 drops of indicator. If you get 3 by mistake, no problem, but at least 2, only 2, okay? Make sure everything is nicely dissolved, all the oxalic acid. It's not going to take too much agitation. All right, and then you set it up. You back up a little bit. And then you set it up just like this. Make sure that everything is going to go straight from the burette into the flask. Now, last week we had a little bit of burette trouble where somebody's burette went like this and a lot of stuff spilled out and we had to neutralize it and it was no problem. But this time around, it's going to be like 50 milliliters of strong base, and that's going to be really dangerous. And also it's going to ruin your titration. So the way that the department recommends to avoid that is whatever your non-dominant hand is, use that to control the burette.